Today we're talking about isomers, and mostly we're going to talk about drawing isomers, but we want to talk a little bit about what isomers are and a little bit about the different kinds of isomers. And we're not going to get too deep into this because there's more to it than we're going to get to, but we just want to kind of focus on the basics, and we'll deal with some of these other things maybe a little bit later as we need to. So first of all, what is an isomer? Well, an isomer, very simply, is two compounds that have exactly the same chemical formula, but they're different compounds because they have a different structure. It comes from two Latin words or Greek words meaning iso, not meaning iso, but iso meaning same, and mer meaning parts, so same parts. So it's a different compound, but they have the same molecular formula. They're also going to then have a different structure, and that would mean they would also have a different name. So one of the things that we're going to do as we go through and sort of double check to see if our isomers are truly isomers is we're going to go through quickly a little bit of, do they have the same name? Or how would I name this one versus how would I name that one? If I give you an example of something like that, so for example here, C4H10, there's a couple different ways I can arrange that. I can arrange it out in one nice long line, and it's not even that long, 4 carbons and 10 hydrogens. If you count them all up, they're all there. Or I could make the chain a little bit shorter and put a branch on it, and where I have C4H10 still, but now they're isomers. So if I were to look at the first one, doing my nomenclature, that would be butane, 4 carbons, alkane. And the second one would be a propane because it's a 3-carbon chain with a branch number 2, so it would be 2-methylpropane. Different name, different compound. Same chemical formula, isomers. Okay, so what do we need to be able to do with them? Mostly what we're going to be doing is recognizing, are these two things isomers? So I'm going to give you compounds and say, all right, tell me if they're isomers or not. And there's basically 3 answers to the question. Yes, they are isomers. No, they are the same compound, so they're not isomers, they're identical, or they're not the same, they don't have the same chemical formula, so they're neither isomers nor identical. We're also mostly going to be spending our time drawing isomers. I'm going to give you a chemical formula. Well, C4H10 is a little bit on the small side, but I'm going to give you a chemical formula and I'm going to ask you to draw isomers, usually 5. And I'll tell you now, the secret to drawing isomers is being systematic. And because if you go all willy-nilly and stuff like that, you're going to end up drawing the same thing twice. I've seen the same thing drawn 3 or 4 times. And that's kind of hurtful when I'm asking for 5 different ones and somebody gives me 4 that are pretty much the same, just drawn slightly differently. That's not an isomer. Okay, starting off with recognizing isomers. Are these two isomers? I should have a ding, ding, ding thing going on here. And the answer is no, they're not isomers because they have a different chemical formula. So there's not the same parts to work with. One is a different number of carbons than the other. Are these ones isomers? You can pause it while you figure this out. These are isomers. So they have the same numbers of carbons and they have the same number of hydrogens. They're isomers, but you'll notice one has a branch where the other one doesn't. How about these two? Are they isomers? Well, you might be thinking, yeah, well, maybe. No, they're not. They're actually the same compound. If I were to take the compound on the right and I were to rotate it, I would pretty much end up with the compound on the left. So, not isomers. They're the same. But this is what I mean. I can draw 2 things, or I can draw one thing 2 different ways, and it ends up looking just different enough that if I'm not a sharp eye, then I'm not going to notice. Okay, how do I draw those isomers to make sure that I'm getting them right? What I would do if I started out with C6H14 is I would start out with a nice long chain, get an idea of what I'm working with. Now in this case, in order to get 6 carbons, 14 hydrogens, I end up with a alkane. At that point, that's actually kind of important information, right? Recognizing the functional group, because now I know that all of the compounds that I draw are going to be alkanes. Now it's not like I could suddenly invent an ether or something out of this, but I could possibly try to draw an alkene or maybe a ring. But if I know it's going to be a straight chain alkane, 2 things. Number 1, it has to be a straight chain alkane now. We'll talk about other options a little bit later, but not for this one. Straight chain alkane. Second thing, to play it safe, Once I know I've got one straight chain alkane, I'm going to keep going with the straight chain alkane theme. Okay, so what do I do next? The easiest way is to draw now a shorter chain and put a branch on it. So I start out with a chain of 6 with no branches. Okay, how about a chain of 5 with 1 branch? Done. 2-methyl pentane. Now, the second thing I can do to try and follow a system is move the branch. So the next thing I'm going to do is I'm going to take that branch, I'm going to move it over 1. So now I've got a 3-methyl pentane. Different name, different structure. Not much different, but it's still different. Now, I kind of want to do that again because that's basically the plan. Make the chain shorter, put a branch, move the branch. Repeat. The problem is if I draw this compound, is it a 4-methyl? No, it's not a 4-methyl because my numbering now has to start from the left end rather than the right end. Which means that's not an isomer because I've already drawn that one. Okay, so I've run out of things I can do with a 5-carbon chain and 1 branch. What do? Shorten the chain, now make 2 branches. So I've got a butane with 2 methyl groups on it. So this would be a 2,3-dimethyl butane. You'll notice I'm not putting the names on here. I'm saying them, but I'm not putting them on here because when you're doing isomers, you don't have to do nomenclature. It's worthwhile to at least think that part through, but you don't have to do it. Okay, is there anything else I can do? Can I make a 3-carbon chain? Can I move those branches? Well, I can't move both of them because they'd end up just swapping places with each other, but I could end up moving one of them. So now I've got a 2,2-dimethyl butane. Is there anything else I can do? No, not on this one. I mean, you can try different things, and you might say, oh, I drew this, but really all you're going to be doing is drawing another version of one of the things that's already up here. Okay, what else can we do with isomers? Well, with the previous one, it was going to be a straight chain alkane because all it was carbon and hydrogens, and the only way I can get 6 carbons and 14 hydrogens is by doing a straight chain alkane. But there are times where I can do different functional groups. So we're going to keep with the hydrocarbon pattern here. I could do a 6-carbon alkene. You'll notice that it's almost the same except with 2 less hydrogens. Something has to give because every carbon has to have 4 bonds. I can't break that rule. The other thing I could do with that is I could wrap it around, and instead of having 2 carbons that are beside each other connected a second time, is I could have one of the carbons on the end connect to the other carbon on the other end, and that would give me a ring. Now, we often draw rings in the more short version where it's just a geometric shape, nice and clean. A little bit harder to count the hydrogens on that one, but it's still doable. Okay. My advice, when you're talking about drawing isomers, is be systematic. Start with the longest chain, move down 1, put a branch, move the branch. Think about how far you can move the branch before you're just repeating yourself. Shorten the chain again, more branches. Sometimes you can do a longer branch rather than just a 1-carbon branch here and a 1-carbon branch there. Sometimes you can go with a 2-carbon branch, but it kind of depends on your chain length because otherwise you're just going to be drawing a long chain that's making weird turns rather than being straight out. Okay. What I mean by that last statement is if I start with this compound and then I try and draw another one and I just go, oh, I'm going to twist it here, I'm going to turn it there, I've actually ended up drawing the same thing. So if I try putting a methyl group on the end carbon, no, it's not going to work. It just makes a chain longer. And if I look at this one here where I've highlighted the carbon chain, it's exactly the same in both. So that is the same compound even though it may not look like it at first glance. Okay, by the time we're done here, obviously you'll want some practice on this one, but you should be able to recognize isomers, and really that comes down to counting the carbons, counting the hydrogens, counting the other things on there to see if they are the same, first off, and then taking a look at the nomenclature. Not necessarily all the time will that work, but generally what you're looking for is longest continuous carbon chain and direction of numbering, and that will usually highlight duplicates that you have. And then drawing isomers. And again, be systematic. Start with the long chain, shorten the chain, put a branch, move the branch, repeat. After that, we'll get some practice in class. Generally speaking, you will always be asked to draw 5 isomers, and I'll always make sure that there are at least 5 possibilities that you have. We may get to talk about a completely different kind of isomer that's a whole lot of fun, but you won't really be required to use it in any of the times that you're drawing. We can always just do structural differences. Okay. Talk to you another time, and see you then.